This video is a review on the chapter of reaction equilibrium in chemical thermodynamics. We start by defining the quantity extent of reaction. So we have the number of moles of a given reactant A in a reaction is equal to the initial number of moles in the reactant minus its stoichiometric coefficient times the extent of reaction. So the change in the number of moles of reactant A is equal to its minus its stoichiometric coefficient times the change in extent of reaction. And then in this video we work through all the way to show that the Gibbs energy of reaction is equal to the partial derivative of the Gibbs energy with respect to extent of reaction evaluated at constant temperature and pressure. The equilibrium constant is defined as a quantity where we have a reaction going from A plus B reactants to C plus D products. We have the pressure, partial pressure of product C to its stoichiometric coefficient nu C times PD times to the power of nu D, and then divided by our reactants of the partial pressure of A to its stoichiometric coefficient nu A times the partial pressure of B to the power of nu B. And all of those quantities evaluated at equilibrium give us the equilibrium constant, which is a fixed number. Our standard Gibbs energy of reaction, delta Rg naught, is equal to minus gas constant times temperature times the natural log of our equilibrium constant, which is a function of temperature only. There are various ways you can express an equilibrium constant. We can do this in terms of partial pressures, Kp, as we did here. We can also do it in terms of molarities or concentrations, Kc. We can do it in terms of fugacities of the gases, Kf, or in terms of activities, Ka, the latter two being referred to as thermodynamic equilibrium constants because they do not depend on any assumptions of ideal gas or ideal solution behavior. Le Chatelier's principle tells us how a reaction responds with respect to some kind of mechanical or thermal perturbation. So if we have the change in the number of moles of gas during the reaction is greater than 0, then if we increase the pressure, then the reaction is going to respond by going backwards. Our extent of reaction will decrease, and some moles of gas will be consumed, and will minimize the effect of that pressure increase. Conversely, if the pressure goes down, then the system responds by going forward in the reaction and creating more moles of gas, thus returning the pressure up a little bit higher. So in each case, the system responds to minimize the effect of the system change. If gas was consumed rather than produced during this reaction, then this behavior would be the reverse. And then in later videos, we show also that if the temperature goes up, then the extent of reaction will go down if you have an exothermic reaction. So temperature going up responds by the system kind of absorbing some heat by going backwards. And if the temperature goes down, then the reaction will go forward and it will generate some heat by releasing it to the surroundings. And this behavior would be reverse if we had an endothermic reaction rather than an exothermic reaction. We can calculate the standard Gibbs energy of reaction from the standard Gibbs energy of formation of the products and reactants. So we sum over all of the products of their stoichiometric coefficient times the standard Gibbs energy of formation for that given product. And then subtract from that sum over all of the reactants, stoichiometric coefficient of the reactant times the standard Gibbs energy of formation of that given reaction, of that given reactant. But the quantity of interest is not the standard Gibbs energy of reaction, but it is the Gibbs energy of reaction. So the Gibbs energy of reaction is equal to the standard Gibbs energy of reaction plus RT times the natural log of the reaction quotient. And the reaction quotient is just the equilibrium, this type of expression which is not at equilibrium. The equilibrium constant is the reaction quotient evaluated at equilibrium. When we're not at equilibrium, it's just called the reaction quotient. So this means that the Gibbs energy of reaction is equal to gas constant times temperature times natural log of the ratio of the reaction quotient to the equilibrium constant. And the reaction Gibbs energy is equal to 0 at equilibrium, which is when the reaction quotient equals the equilibrium constant. So the spontaneity, as I said, is determined by the sign of the Gibbs energy, and it tells us what the extent of reaction is going to be. If the Gibbs energy is less than 0, Gibbs energy of reaction is less than 0, the reaction goes forward. If it's greater than 0, the reaction goes backwards. And if it's at 0, then the reaction is at equilibrium and it doesn't move in either direction. And then there's also temperature dependence, which depends on the sign of the enthalpy and the entropy of reaction as well, determining whether it's spontaneous at low temperatures, at high temperatures, or at all temperatures, or at none. We can then determine how the equilibrium constant changes with temperature by using the Van't Hoff equation, which came from the Gibbs-Helmholtz equation. It says that the natural log of the equilibrium constant at temperature 2 divided by equilibrium constant at temperature 1 is equal to the negative standard enthalpy change of reaction divided by gas constant times 1 over temperature 2 minus 1 over temperature 1. So the standard enthalpy change of reaction is just equal to the amount of heat that is absorbed or released by the system during the reaction. So if you plot, for example, the natural log of the equilibrium constant that you measure at two different temperatures, so plot natural log of equilibrium constant versus the inverse of temperature, what you'll get then is a straight line, and the slope of that straight line will be the negative enthalpy change of reaction divided by the temperature. So you can actually get what the standard enthalpy change is by calculating the equilibrium constant at two different temperatures and then plotting. And that should be actually, this should be R, not T. So I'll go ahead and correct that. Okay, then finally we have condensed phase activity, which tells us why it is that in expressions for equilibrium constants we often leave off solids and liquids. So the activities for solids and liquids are assumed to be approximately constant, and it's because their molar volume is approximately constant. We calculate that the natural log of the activity for a given solid or liquid is equal to its molar volume times the pressure minus 1 divided by gas constant times temperature. So if we're at values of pressure which are approximately at 1 bar, this molar volume is approximately constant, and so the natural log of the activity is approximately 0, given that we have this pressure being approximately 1 and this value being constant. So the natural log of the activity being 0 means the activity is approximately 1. So adding in the activity of a solid or a liquid in an equilibrium constant would just be effectively multiplying by 1.